All right, in this section, we're going to start tying all the things we've been learning together into one theorem. And we've seen the start of this theorem. We're just now adding all the things that we've learned recently to it to create a longer list. And we'll keep adding to it every section where we usually tack one or two things onto this theorem. And so it's a really sort of overarching big theorem in linear algebra. Anyone who takes linear algebra is familiar with this theorem. And these are all the things that you sort of want to take with you as you move on to other classes out of linear algebra. So basically, this is called the invertible matrix theorem. I oftentimes abbreviate it with just IMT, as I've already mentioned before. And this theorem is only for square matrices. So it needs to be square n by n matrices because we're talking about things like determinants. Well, I guess we haven't learned about determinants yet, but things like determinants and eigenvalues and things like that only apply to square matrices. So we're talking about a square n by n matrix for the invertible matrix theorem. And what it says here is all these things are equivalent. In other words, they're either all true or they're all false. And so when you know one of them's true, you know they're all true. And if you know one of them's false, you know they're all false. Right? So i.e., if one's false, they're all false. That's what it means to say they're equivalent. And if one is true, they're all true. And so it's a very powerful theorem because if you know one of these things, you know lots of other things about a matrix. That's sort of the general idea. And what I'd like to do on this page to start is just sort of give you an idea about how some of these things are tied together. Like as you read through these things right here, and I would encourage you to take a second and just read through them, so you have an idea of the type of things we're talking about. So let me just talk about a couple. So A being invertible is equivalent to it row reducing to the n by n identity matrix. That's just the definition of being invertible, right? Those two things. It also means that there's a pivot in every row because there's n pivots, right? Well, that means there's n pivots because there's one in every row. And that leads to the on 2 and G. There must be a solution for every B and Rn. That also means that if there's a pivot in every row in a column, that means there's no free variables. If there's no free variables, that means there's only the trivial solution to the homogeneous equation, which is B. It also means E. It means that there's only the trivial solutions. That's how we figure out if things are linearly independent, et cetera, et cetera, et cetera. So like once you start sort of going through these things on the time, you can start seeing how one just sort of leads to the other, which leads to the other, which leads to the other. And so I'd like to give you just a little bit of an explanation, tying a few of these things together at the bottom of this page. And then the next couple of pages are some examples of how we use this information in practice. So a couple explanations here. So A says, letter A, that is, part A says that if the matrix A is invertible, then all these other things are right. So A, if A is invertible, if a matrix A is invertible, by definition, that means the inverse exists. If we know the inverse exists, by definition, the inverse, a to the minus 1, is something you can multiply by A to get the identity matrix. So right away, we get J and K just from A inverse. So we could say, if A inverse exists, then that means you can multiply it by A to get I on either side. And so if we know the inverse exists right away, this one is part K, and this one is part J. Let's see what D leads us to. So D tells us that the equation AX equals 0 has only the trivial solution. So let's write that down and see if we can reason why a couple of these other things follow from that. So D tells us, part D says, actually, let me just finish off with A. The other thing that A just tells us really quickly is that if we know the inverse exists, then that means the transpose also has an inverse by theorem 7. So the other thing we know is like if A is invertible, part A tells us A is invertible. And so if we know that A minus 1 exists, that means so does the transpose inverse by theorem 7. And so that's how we get part L. I just wanted to mention that before we move on to part D. So part D says that AX equals 0 has only the trivial solution. So if that happens, so if AX equals 0 has only the solution X equals 0, right, the trivial solution, that leads to a whole bunch of things. For one thing, that's how we figure out if things are linearly independent. If you look back at the linear independence section, we looked for linear dependence by seeing whether or not AX equals 0 had a non-trivial solution. And so by definition, by what we talked about with the linear independence, this automatically means that the columns of A form a linearly independent set. And so we automatically get part E from that. If we know it only has a trivial solution, which means the columns are linearly independent, that means there has to be a pivot in every row, right? So if we only have the trivial solution, we need a solution for every variable, and that means there's a pivot in every variable spot, which means there's a pivot in every row. And so this also leads to, it also means there must be a pivot in every row. And that's one of the parts as well. That's part C. And then, oops, I'm realizing off the page here. And then if we know if there's a pivot in every row, that leads to lots of things. So if there's a pivot in every row, this implies a whole bunch of things. It implies that A spans Rn, that's part H. It implies that there's always, spanning means AX equals B always has a solution. A solution. And it also means, by definition, that A is on 2. All these three things kind of mean the same thing. A spanning Rn, always having a solution, and being on 2 are all the same way of saying the same thing. And so that A spanning Rn was part H, this one was part G, and this one is part I. And so, you know, AX equals 0 having only the trivial solution leads to a lot of things right away. Having n pivots also leads to some other things here. So let's finish up with C. So we know there's n pivots. So if there's n pivots, which is what C says, and we already came up with C right here, right? This is that followed from AX equals 0 having the trivial solution. So if there's n pivots, then that means there must be a pivot in every row because there's n rows. And if there's a pivot in every row, that means we have no free variables. And if there's no free variables, that means A is 1 to 1. And it also means all rows have a pivot, which means A is on 2. I know we already said that previously, but just another way to think about it. Right? This is how we thought about 1 to 1 and on 2. We thought about on 2 as being pivot in every row, and we thought about 1 to 1 as being no free variables. So we get 1 to 1 and on 2 as well, which are letters I, this one's I, and 1 to 1 is F. And so just kind of showing you how these things are all tied together, right? A leads to K and J. A also leads right to L. If D leads to E, C, H, G, I, et cetera, et cetera. And they're all kind of tied together in a very similar way. And hopefully, if some of this makes sense, you can kind of see how they're all tied together. And usually, I would recommend, I mean, you're going to need to know this for a test. But the thing, and the question, type of questions that oftentimes get asked on tests are the ones that are on the next couple pages, which are also similar to the ones that are in the homework. And in order to memorize this thing, you can just sort of beat it into your head and memorize it, or you can kind of do what I'm doing down here, which is seeing how all these things really do lead to each other. And then you don't really have to memorize it. It just kind of makes sense. And you can think about, well, if this happens, then that means this is true, which means this is true, which usually leads you down the correct answer. And you'll see what I mean by that in the next couple pages. I will show you at least one or two of those examples, and then I usually ask people to think about the rest of them on their own. I will be going through all of them in this particular video. Okay, so let's turn the page and start looking at that. So you can see here, labeled as an in-class activity when I teach this in class. Like I mentioned, I usually do the introduction I just gave, and then I let students think about these on their own, although I usually do one or two examples. So that's what I'm going to do here is maybe go through one or two on this page, and then let you think about the other ones a little bit, and then I will go through all of them afterwards. So what you want to do is use the invertible matrix theorem where applicable, answer these questions. The first question says, is it possible that we have a 5 by 5 matrix that's invertible, but its columns don't span R5? And so right away, we can just go back to the invertible matrix theorem, and we see that we're being told that the matrix is invertible, so A is true. So that means all these things are true. And so do the columns span R5? Well, H is true because A is true, right? So we're being told A is true, so that means H is true. And so you can, if this is a test or something, and I wasn't requiring some explanation. We know that since A is true, H must be true. But let's just go ahead and explain why that's true. Let's give it a little bit of a background. So the answer here is, and it says why or why not. So I'm asking for more than just quoting the theorem or just giving an answer. So the answer is no. So let's talk about why. Well, we know that if A is invertible, then that means it reduces to the identity matrix by definition of being invertible. So if A is invertible, then that means A reduces to the 5 by 5 identity matrix. So I sub 5 would be the 5 by 5 identity matrix. And so we know that's true. And so if it reduces to the 5 by 5 identity matrix, well, the 5 by 5 identity matrix has a pivot in every row. So I5 has 5 pivots, one in each row and column for that matter. But the row part's important because if we know we have a pivot in every row, by definition, that means it spans Rn. And so it does span R5 again because we have a pivot in every row. So if we have a pivot in each row, 5 of them, then that means A must span R5. And so, the theorem gave us the answer right away, but tying the things together is kind of the important part behind this theorem and this process. Let me look at another good one here to think about here. Let's do the second one. I don't really see another one that stands out to me. Let's look at the second one together again, and then maybe you can think about the other ones. So the second one says, if we have square matrices, n by n matrices, E and F, and they have the property that you can multiply them together and get the identity matrix, then E and F commute. And the word commute means that you can multiply them. It says right here, that is, EF equals FE. Explain why. So I'm actually saying it's true and asking you to explain why. So this right here, this E times F equals I, is the key part. If we know E times F equals I, that looks like parts J and K here. So we're being told that there's some matrix that you can multiply to get I. Well, that means that the matrix is invertible. So we're being told J, which means the whole thing is true, which means A is true, right? And so if we know that, say, in this particular case, E and F commute, let's say we're being told J, well, that means that K is also true. And so you can change the order of them because they're each other's inverse in this case, and you can multiply on either side and get I. And so the answer to this is a yes. I mean, we're being told yes, but just to be clear, the answer is a yes, if they do commute. And the idea is, if we know E times F equals the identity matrix, then that means both E and F are invertible. And so E and F being invertible, this is parts J and K of the invertible matrix theorem. And not only are they both invertible, they're each other's inverse because you can multiply them together and get the identity matrix. And so not only are they invertible, but they're also each other's inverse. In other words, E is F inverse. And so that means when you multiply E times F, you're really doing E times E inverse. What? I should have written it the other way. Sorry, let me rewrite it so this makes sense. E is F inverse, so let me do it this way. So I'm going to replace E in this with F inverse. And so you'll have F inverse times F. And we know F inverse times F is the identity matrix, the square and lambda identity matrix. And moreover, you can multiply it on either side. If you did F times E, again, you can replace E with F inverse. That's just F times F inverse again, but the order switch. And that's a situation where matrices do commute. You can commute the inverses. And so, in other words, since E times F is the same thing as F times E, in both cases you get the identity matrix. This means that E times F equals F times E, i.e. they commute. And these are the type of questions that you'll see. Again, they're in the homework. I always put questions like this on tests. Sometimes they're sort of like true-false questions where you correct them and write the right answer. Sometimes they're just literally like this, where I say, hey, use the invertible matrix theorem, or I may not even specify use the invertible matrix theorem, and say, see if you can reason. If I give you one piece of information, can you reason some other piece of information? And so, there's 2, 4, 5 more problems in this particular section, and I would really strongly encourage you to take 15 or so minutes and work through them yourself. See if you can get some answer written down for them. Maybe keep it in pencil in case you're not super sure. Just pause the video, think through them, try to relate them back to the IMT on the first page, and see whether or not they're true. I'm going to keep this video short today in anticipation that you're actually doing that work. And I'm hoping that you'll do that. And then the idea here is if you get them right, wonderful. But if you get them wrong, hopefully you had thought about it already a little bit. And then when I go through them in just a second here and explain them, it'll make more sense. So this is a really good opportunity for you to try this. I really strongly recommend you do that and hope you do. So just pause the video now and take a few minutes and think through the next 5 questions. When you're ready, unpause and I will go through them. All right, I'm going to start to go through them, starting with number 3. And so number 3 says, if the equation hx equals c is inconsistent for some c in R4, so this doesn't have a solution, in other words, what can you say about hx equals 0? Does it have a non-trivial solution? Why? Assume h is 4 by 4. So h needs to be 4 by 4 so that we can do this multiplication. Excuse me. But what we're basically being told is we're being told something about part G. We're being told that the equation ax equals b has at least one solution is not true. So we're being told that this is a false statement, G, and so that means they're all going to be false. So let's start by writing that down here. So if hx equals c is inconsistent, then that means part G of the IMT is false. i.e. hx equals c has no solution. Well, this is going to imply that all the IMT is false. So this implies all of IMT is false. And if the entire IMT is false, what does it say about hx equals 0? Well, hx equals 0 then is not going to have only the trivial solution, right? In other words, it's going to have a non-trivial solution. Let's write that down. So that means if they're all false, this implies all the IMT is false. That means hx equals 0 has a non-trivial solution, so it has a non-zero solution. If it has a non-zero solution, that means there must be a free variable. Right? So the other way to say that is one of the things in the IMT is that there's no free variables, right? N pivots, and so if there is a free variable, means, excuse me, if they're all false, then this means that it has not n pivots, which means there's a free variable. And if there's a free variable, that means that AX equals 0 is going to have infinitely many solutions. Right? And so this means H has a free variable. I mean, we didn't need to use the IMT for that, right? If AX equals 0 has a non-trivial solution, we know it has a free variable by definition. And so it has a free variable. And so that means there's going to be a non-zero solution here. In other words, it's going to have infinitely many solutions. So that's how we could think about number 3. Just say one more time. Since hx equals c is consistent, the IMT is false, and so we already know it has no solution. And so that means everything's false, and so hx equals 0 has a non-trivial solution since the IMT is false. If it has a non-trivial solution, that means there must be a free variable. If there's a free variable, that means there's infinitely many solutions to hx equals 0. Okay. I will flip the page here and look at number 4. And number 4. Number 4 says, suppose L is a square matrix and Lx equals 0 has the trivial solution. Do the columns of L span Rn? Why? This one is something of a trick question. See, now it says that it has the trivial solution. Well, this always has the trivial solution, right? You can always plug in x equals 0, multiply it by a matrix, and get the 0 vector. And so the trivial solution is always true. So just saying it has it isn't saying anything. What the IMT says is that it has only the trivial solution, right? And that word only is not here. And so the first thing we should note is that x equals 0 is always solution. We don't really have enough info here. So the trivial solution, which is x equals 0, is always true. And so there's not enough info here to answer this question. Let's say the word only was in there. So let's say it said Lx equals 0 has only the trivial solution. If it said only the trivial solution, then that would mean part B is true, which would mean the whole thing is true, which would mean that there's a pivot in every row and the columns would span Rn. So with that word only, we get all of them being true, which in particular gives us H, which is the answer to this one, right? And so let me write that down. If it said Lx equals 0 has only the trivial solution, then that would mean all of the IMT is true. And if all the IM2 is true in particular, there's a pivot in every row. it means there's a pivot in each row. And if there's a pivot in every row, that means the columns are linearly independent. And they span Rn. And so if that word only was in there, then we'd get a double true situation. But since the word only wasn't there, we would have to say there's not nothing. I wouldn't do a tricky one like that. If that's something, it'd be a yes or no, not a, ooh, maybe if this word was here. But just wanted you to think about that one a little bit. Okay, let's think about the next one. So number 5 says, if we've got a square matrix whose columns are linearly independent, explain why the columns of A squared span Rn. Well, if the columns are linearly independent, then that means E is true. And if E is true, they're all true. In particular, A is invertible. And if A is invertible, we learned in the last section that multiples of it are also invertible. So A squared would also be invertible. And if A squared is also invertible, that means the IMT true for A squared, which means the columns would span Rn. That one involves something from the last section, a little bit outside the IMT, but still a good question here. So the idea here is if A has columns, linearly independent columns, that means A is invertible by the IMT. And if we know then A is invertible, then A squared, which is A times A, is also invertible. In particular by theorem 6 from the inverse section. And that implies, this arrow means implies, that implies all of the IMT is true for A squared. And if all of the IMT is true for A squared, this implies that A squared has columns that span Rm. N, excuse me. Because that's one of the IMT. That is H, part H of the IMT. All right, number 6. Number 6 says, if we have a square matrix A, and the transformation that sends X to AX, that's how you read this. It's a transformation that sends X to AX, and we're being told it's 1-to-1. So here's the key thing here. The 1-to-1 transformation. What else can we say about the transformation? Well, lots of things. Because if it's 1-to-1, well, that's part F right here, right? The linear transformation X to AX is 1-to-1. And so we have that being true. And so that means everything's true. So we can say all kinds of things about this transformation. All these things we can say based on that one piece of information, right? So this right here is condition F in the IMT. And so if that's true, all of the IMT is true. So all the IMT is true. And so we can say lots of things about A. A is on 2, for example. That's one of the things. A is invertible. Right, we could say AX equals 0 has only the trivial solution. That's one of the parts. We could say that AX equals B has only one solution for every B. Those are both parts of the IMT. And then moreover, if it only has one solution, that means the definition of being 1-to-1. And if it happens for every B in Rn, that's the definition of A being on 2 and spanning Rn. Right, and so just as an example, we can say everything in the IMT is true. Those are just a few examples of the things. Okay, the last question here tells us we have got a linear transformation that sends vectors from Rn to Rn. As a quick reminder, it needs to be the same Rn in both those because we need a square matrix to use the IMT, right? So Rn to Rn means we have a square matrix. Okay, so let's say that the transformation has the property that T of u equals T of v for some pair of distinct vectors. In other words, different vectors. Can T map Rn onto Rn? Why or why not? So two different vectors having the same linear transformation is the definition of not being one-to-one. One-to-one means that every vector gets sent to its own location. And so this is two distinct vectors getting sent to the same place. So in other words, the IMT is false in this case. So if T of u equals T of v, then T is not one-to-one. And so that means all of the IMT is false. If all of the IMT is false, that means it's not invertible, it doesn't span, etc. So T is not invertible. It does not span Rn, etc. We know all the things in the IMT are false. In particular, one of the things in the IMT is on2, right? And so, let's see here, where is on2? I, right? Linear transformation is on2, so that must be false as well. That's going to answer this question. So is it on2? No, because the IMT is false. This means T is not on2. Okay. And so just some examples again of how we can tie all these things that we're learning about in linear algebra together and relate them to each other. It's really, really, this is my favorite thing about linear algebra. Everything's just tied to each other. It's all about row reducing and looking at pivots and things. And the cool thing is if you have a good understanding about what's going on, then you should be able to tie all these things together without too much of an issue. Okay. The last thing I'd just like to talk about in this section is just, there's not too much on this page here, but it's just talking about invertible linear transformations. So relating this back to linear transformations. We talked about linear transformations in sections 1.8 and 1.9. And what we had said was every linear transformation T of x can be written as an n by n or m by n matrix A. And as a quick reminder here, so this is the sort of thing we saw in that section, right? Every transformation can be written as matrix multiplication. And generally speaking, when we were talking in 1.8 and 1.9, we were talking about taking things out of the domain, which is where you plug things in from, and sending them to the range over here. And so multiplication by A, which is the transformation, T, is going this way. Well, what I'm talking about in this page is going the other way. If you multiply by the inverse of A, it'll take things back to X. But in order to talk about this having an inverse, we need to talk about a square matrix because you can see that we need to have the inverse of the matrix, and only square matrices have inverses. And so that's why right here we're talking about Rn to Rn. We need to have a square matrix because we want it to maybe be invertible. Okay. So if we have something from Rn to Rn, it's invertible if and only if there's some function that undoes the transformation and sends things back to X. That's what this one says. And again, we need A is a square matrix in this case because only square matrices have inverses, which means that only square linear transformations represented by square matrices will have an inverse. And so in other words, since any linear transformation can be written as a matrix A, whether or not that transformation has an inverse really boils down to whether or not A has an inverse. In other words, we know that T of x equals AX. That's sort of the definition here. Then that means A minus 1, A inverse, is the inverse of the transformation. And so this theorem tells us about when that happens. So let T be a linear transformation from Rn to Rn, so square matrix. Let A be the standard matrix that represents it. T is invertible if and only if A is invertible. Makes sense? In that case, the linear transformation that sends things back is going to be the one satisfying those two equations, and it's going to be given by A inverse. And notice why it's given by A inverse. Notice what happens here. So we know, so notice. We know that T of x equals AX, right? That's the definition of a linear transformation. And when we do AX, it's going to equal some other linear transformation B, right? So when we do A times X, this is going to be some other vector B. Well, if we want to undo that, then we need to multiply this by the inverse on the left, right? So we multiply by A minus 1 on the left. These two things cancel into I. And so what we end up with is we really just get I times X equals A inverse B. And anything times I just stays the same. And so X equals A inverse B. Right? So if you want to send things back to the X values they came from, do the inverse. You just multiply where it came from by the inverse to undo it, is what we're saying here. And so it's just a nice little application of matrix inverses, which is why we wanted to talk about it right after that inverse section. Okay, that's all I've got for this particular video. Please do reach out with any questions, and I'm happy to talk to you either during our scheduled class time or outside it if necessary.